Welcome to Making a Splash, Nitazenes and Orphines, the latest wave of opioid NPS. My name is Danny St. Germain, and I'm a synthetic organic chemist in the Forensic Chemistry Division at Kamen Chemical. In this webinar, I'll be covering the two benzimidazole opioids referred to as the nitazenes. I plan to go over where they came from, how we name them, how they're made, and how to identify them in EI mass spec samples. I'd also like to provide a snapshot of the most recent emerging scaffold, the piperidinylbenzimidazolone opioids, colloquially referred to as the orphines. The nitazenes are a common name for the class of 2-benzyl-benzimidazole opioids. They're called that because their core is this benzimidazole, with the one position being this nitrogen that can be substituted, and the two position located between both of the nitrogens that can be substituted with this benzyl substituent here. Now, this series of compounds was originally developed in the 1950s at the Swiss company Ciba. They developed a series of these analogs and found that they were potent analgesics, with this compound adenitazene being magnitudes of order more potent than morphine. And as you can see, this compound does not look anything like morphine. The opioid activity of the nitazenes depends on the three major sites of modification on its scaffold. We have this ethyl amino substituent located here at the N1 position. We have this benzyl substituent here in orange, located at the 2 position. And then, of course, we have our benzimidazole group, typically with a nitro group here at the 5 position in blue. Now, modeling studies suggest that the ethyl amino substituent mimics the piperidine ring in morphine, while the benzimidazole overlays the benzofuran ring system in morphine. You can see that they overlay. They also suggest that the substituents in the para position on the benzyl ring, located here at this point, here on your benzyl group, this locks the compound into place, which increases its specificity to the mu opioid receptor. So the potency of adenitazene is attributed to those two ethyl substituents located at the ethyl amino position, and then the para ethoxy substituent on the benzyl group. Once the blanket regulation of fentanyl analogs went into effect in 2018, the race was on to fill the void, and isodonitazene was found being discussed on Reddit threads in February of 2019, and multiple detections yielded a CFSRE monograph by October of 2019. Since then, the market has proliferated with multiple analogs. Nitazenes are being detected in counterfeit tablets and are being found marketed as different classes of drug altogether. Metanitazene was detected in counterfeit oxycodone tablets in Ireland, Slovenia, Sweden, Finland, and Norway during the years 2021 to 2023. 150,000 tablets containing an unspecified nitazene was seized in the UK in October of 2024. And a sample from a user in Nashville, Tennessee was found to contain 100% adenitazene. And this compound was marketed as 2-oxo-PCE, which is an aerocyclohexylamine similar to ketamine. So that's a completely different class of compound, and the user would be expecting a completely different experience, which makes this even more dangerous. And according to the DEA Street Report from January of 2024, the presence of nitazenes in fentanyl, heroin, and cocaine submissions has been on the rise. In 2021, we collaborated with a Stove group at Ghent University to look at the harm potential and pharmacological profile of a series of nitazenes that had been detected in forensic samples, as well as sold on direct-to-user sites, and their presumed metabolites. The mu opioid receptor is the receptor that is responsible for the perceived euphoria and respiratory depression associated with opioids. These assays give results in nanomolar concentrations, which means that it takes very little of the drug to activate the receptor. The lower the number in these assays, the more potent the compound. Think of it like a golf score. The lower the score, the better the player is at landing the ball in the hole. And the lower the number here, the better the drug is at binding to the mu receptor. All 12 of the nitazenes that we tested were more potent than morphine, and 5 of them were more potent than fentanyl. isodonitazene with this isopropoxy group at the para position of the benzyl substituent is 10 times more potent than fentanyl at more. And when compounds are metabolized in the body, they are typically made more inert and less toxic so that they can be eliminated. And this metabolite of isodonitazene loses an ethyl chain and forms N-desethyl isodonitazene. So we were very surprised to find that the N-desethyl isodonitazene was even more potent of an order of magnitude than its parent isodonitazene, which is more potent than fentanyl by an order of magnitude, making this about 100 times more potent than fentanyl. The beta-arrestin recruitment in isodonitazene is the reason why these compounds are so dangerous, because this is the main culprit behind respiratory distress in opioid and overdose victims. So mirroring our results, another research group, Malcolm et al., investigated N-desethyl isodonitazene in mice and found that the respiratory depression and recovery time lasted much longer than fentanyl. So here it took about 4 micrograms of N-desethyl isodonitazene versus 11 micrograms of fentanyl to halt respiration altogether. And after giving these mice naloxone, it took 30 minutes for fentanyl dosed animals to recover all their respiration to 100% versus 300 minutes for those animals that were dosed with N-desethyl isodonitazene. So these are my studies, and while this is not a direct translation to humans, to give you a rough idea of what these numbers could mean, it might take less than half of a milligram of N-desethyl isodonitazene, a dose invisible to the naked eye, to stop the breathing of a 220-pound mouse. And this is why we wear lab coats, protective eyewear, gloves, and dust masks in our lab when handling this class of compounds. N-desethyl isodonitazene is not just a metabolite. It is now also heavily trafficked on direct-to-user sites and has been detected across the country. According to the CFSRE's 2024 Q2 report, multiple detections have been found in Colorado, Texas, Tennessee, in the East, in Pennsylvania, Connecticut, New Jersey. And nitazene detections are up across the country, with N-pyrrolidino modified analogs being heavily detected as well. One of the challenges with newly emerging scaffolds is, what do we call them? Because we're the first to synthesize the reference standards, we're also often the first to name them. We collaborate with stakeholders in the forensic community to come up with a workable naming system for these new compounds. And I'd like to send a special shout out to Alex Krotulski at the CFSRE. We work with him frequently, and our collective goal is to make these structures readily identifiable based on a simple naming system. When it comes to nitazenes, there are no hard, fast rules, but more trends that we follow as analogs present themselves. Now, referring back to the scaffold that we already discussed, the term nitazene indicates that there's the benzimidazole core with a nitro group at the 5 position, a benzyl substituent at this 2 position, and ethyl amino group that is substituted with 2 ethyl substituents. And the benzyl substituent often has an additional substituent at its para position. So we'll first look at how the benzylic group substitutions tie into the core name. When there's a substituent at the benzylic group, we add the abbreviation of the substituent and place it in front of the word nitazene, such as edonitazene. That means that there is an ethoxy group at the para position, and that there's a nitro group at the 5 position, making it edonitazene. When the alkoxy groups are swapped, we have a shorthand for each chain: meto for methoxy, proto for propoxy, isoto for isopropoxy, buto for butoxy, etc., and so on. Now, sometimes names are already circulating and we get locked into them, such was the case with nitazene, where a methyl substituent was substituted at that 4 position and was abbreviated to ME. So when propylnitazene came out, we had to think about a different suffix because pro is the common abbreviation for propoxy groups. So pronitazene could be mistaken for having a propoxy group, which would be the same as protonitazene. So we agreed to expand the subsequent alkyl chains to their full name to better differentiate them from their alkoxy cousins, making it propylnitazene. Some names from direct-to-user sites stick, such as the case with fluetinitazene, indicating that there is a fluoro group on the etonitazene chain. And some result in lively discussions with multiple options, as was the case with this ethylene oxynitazene. We kind of tied ourselves in knots on that one before we finally settled on the simplest options. So this constitutes the core name of nitazenes that we will modify moving forward. Moving on to benzimidazole group modifications. Recall that the term nitazene indicates that that nitro group is located here at the 5 position on our scaffold. If the nitro group on the benzimidazole is swapped out, we keep the core name that we discussed earlier, but we add des, meaning without, in front of the nitazene to indicate that the compound is without that nitro group. It can also be named des-nitro as well. So instead of des-nitazene, it would be a des-nitro nitazene. If we look at the benzyl substituent, which has a propoxy group here, that makes this protonitazene, but there's no nitro group at the 5 position. So we would modify this name to proto-desnitazene. If the nitro group is swapped out for a different functional group altogether, we must first add the position of the substituent on the benzimidazole, then the substituent abbreviation, and front of the term des modified core name. So here we have an ethoxy substituent located at the para position of your benzyl group, making it etonitazene, but there is a methyl substituent on the benzimidazole at the 5 position, making this 5-methyl eto-desnitazene. So far, we have only seen nitro, methyl, and unsubstituted benzimidazoles. Changes on the ethylamino group take beats from tryptamine nomenclature rules. Now, as we discussed earlier, that ethylamino group is typically substituted with 2 ethyl chains on the amine. When one of these ethyl chains is missing, we add a des-ethyl to the front of the core name, again, des meaning without, and des-ethyl meaning on the nitrogen without an ethyl group. And by adding one N, we are indicating that it is monosubstituted. So here we have an ethoxy group at the para position of our benzyl substituent, making it etonitazene. But we look at the ethylamino group and there is only one ethyl chain, so we would then call this N-desethyl etonitazene. When both of the ethyl substituents are swapped out for 2 methyl groups, we add NN to dimethyl to the front of the core name, and we add 2 N's to indicate that it is disubstituted, making our modified structure NN dimethylamino etonitazene. When heterocyclic amines are swapped in, we add N-pyrrolidino for pyrrolidino substituted compounds and N-piperidinol in front of our core name for 6-membered heterocyclic rings with nitrogen. And there's only one N because the heterocycle is assumed to be connected twice. So one example is this N-piperidinol etonitazene with the ethoxy substituent at the benzyl position. Again, the nitro group is located on the benzimidazole, and then we have the N-piperidine, so we have N-piperidinol etonitazene. And then if we look at this structure, we have, again, the ethoxy substituent making an etonitazene. We're missing a nitro group here at this benzimidazole 5 position, making it an eto-desnitazene, but the ethylamino group is substituted with a pyrrolidine, so that makes it N-pyrrolidino desnitazene. Other names are often used in direct-to-user websites, and this class of opioids is often referred to as zenes on user threads. So those N-pyridinol analogs that we just discussed are often referred to as nitazepine or nitazepines. The N-piperidinol analogs are known as nitazepipne. So we have etonitazepine and then etonitazepipne. Fluetonitazene, which came out late in 2024, that is also referred to as F-etonitazene. And then etodesnitazene was heavily marketed as Etazine or Etazine. And then the 5-methyl etonitazene was marketed as etomethazine. Now, the scaffold of these opioids are relatively simple and they're easy to manipulate. Like fentanyl, a wide variety of analogs is possible, making them attractive to the clandestine chemist. There are 2 direct pathways to synthesize these compounds from cheap, commercially available starting materials. The first path involves the coupling of an aniline with an ethylene diamine to form this dianilino intermediate, and that is followed by a coupling with a benzylic carboxylic acid, followed by cyclization to form the final product. Now, what's important about this route is that it installs the benzimidazole substituent R1 at the 5 position on the final product. The second method is very similar, but in reverse order, where the benzimidazole is first formed through coupling and cyclization. Then it is alkylated with an ethylamino substituent with an appropriate leaving group. And then because this double bond can isomerize and bounce back between N1 and N3 through tautomerization, this allows alkylation to occur on the top and the bottom of the benzimidazole. So this causes kind of a stereo scramble where you have the R1 being installed at both the 5 and the 6 position on the final products. And in December 2023, Bavarian State Police seized a sample containing a 3-to-1 mixture of the 5 and 6-methyl etodesnitazenes. So it's highly probable that this mixture came from this second method of synthesis. So now that we know how they're named, how they're made, let's look at how to identify them in EI mass spec samples. Nitazenes have a very distinctive EI mass spec fragmentation characterized by this huge base peak and maybe a couple smaller peaks and a whole lot of grass at the baseline. The molecular ion may or may not be present depending on the structure, and many of these analogs also have similar fragmentation patterns, making it very difficult to differentiate between them. The nuances are often found in the baseline and require pumping up the volume to access these lower abundance fragments. Here we have one of the latest nitazenes on direct-to-user sites, and we'll use some tips and tricks to identify the structure from the fragments we can detect. Before we begin, I'd like to point out the excellent hard work of Emma Hardwick and Tyler Davidson at Sam Houston State University. They recently published their work elucidating the fragmentation pathway of this class of compounds in the journal Forensic Chemistry, and I will be leaning heavily on their work in subsequent slides. It is an absolute must-read for the forensic chemist. In general, they describe 4 fragmentation pathways in nitazenes, and we'll use etonitazene as our main example. Alpha cleavage that occurs between the bond from the benzimidazole and the ethylamino chain results in iminium ions. And those iminium ions can occur on the benzimidazole portion and the amine portion. And then we have phenylic cleavage, and that occurs at the bond adjacent to the phenyl group and the it forms this phenyl ion. And then we also have benzyl cleavage that occurs at the bond adjacent to the benzimidazole, and that leaves these benzyl fragments. And each of these intermediates can undergo a subsequent 4-center elimination to form secondary fragments. We'll begin with the most common fragmentation portion seen in spectra, the alpha cleavage of the amine. Now, this is the pathway that's most responsible for that base peak. The base peak is this iminium ion of the substituted amine, and then force center elimination removes one of those substituents to form this secondary iminium ion. Now, these iminium ions are incredibly stable, which is why they're so abundant. Alpha cleavage can also leave this benzimidazole portion charged. And these fragments have lower abundance, but if they are present, they can provide vital clues for the substitution on the benzimidazole and the phenyl ring. The most common base peak in this class of compounds is that NN diethyl substituted iminium ion with an M/Z of 86. This ion will then fragment further to N-disethyl iminium ion through force center elimination to form M/Z of 58. The tertiary iminium ion is more stable than the secondary counterparts, so that force center elimination ion will be less abundant. But if you see a base peak of 86 and a secondary fragment of 58, you can be pretty confident that this amine is substituted with two ethyl groups. If you see M/Z 86, but you don't see 58, then another substitution pattern could be possible, such as an N-methyl and propyl substitution. Now, something to note on all of these fragments is that a loss of hydrogen from these ions can occur, resulting in an M/Z -2 of both or either of these fragments. The heterocyclic amino substituents fragment the same way, with the alpha cleavage resulting in the iminium ion base peak. Now, pyrrolidino analogs will form a base peak of 84 with this pyrrolidino iminium ion, and piperidinal analogs will form a base peak of 98 with this piperidinyl iminium ion. The pyrrolidino iminium ion undergoes a ring collapse through force center elimination to form the cyclobutyl cation at 55. So a combination of a base peak of 84 and a secondary peak at 55 is diagnostic for a pyrrolidino substituted nitazene. Similarly, the piperidinyl iminium ion, which is difficult to say very fast, it can undergo force center elimination pathways to two products. It can form the cyclobutyl cation at 55, as well as an azidinium cation at 70. So the combination of a base peak of 98 and in the presence of 70 and or 55, it's diagnostic of a piperidinyl substituted nitazene. Again, a loss of hydrogen can occur, resulting in an M/Z -2 of one or more of these fragments. In our unknown spectrum, we see that we have a base peak of 86. And if we look upfield, we also see a peak at 58. So the combination of 86 and 58 are diagnostic for diethyl substitution on our ethyl amino portion of the compound. Exploring the rest of the spectra, we see that we have a couple of peaks above baseline. We have this 107, and we have a peak at 153, and those are going to help us identify the substitution on the benzyl portion of the molecule. The benzyl group can undergo two types of cleavage. This minor pathway is the phenylic cleavage, where it fragments at the bond adjacent to the phenyl substituent, forming this phenyl ion. But this ion is typically not observed above baseline. So we'll focus on the major pathway, which is the benzylic cleavage, which occurs at the bond adjacent to the benzimidazole core. This benzylic cleavage leads to this benzylic ion, and benzylic cleavage is more abundant in N-diethyl analogs, but we'll talk about that more a little bit later. Benzyl groups with alkoxy chains that are longer than methyl can undergo benzylic cleavage and then undergo a further force center elimination to form this phenolic cation. And because of the pharmacological properties of these compounds, we assume that the substituent is on the para position of the benzyl group initially. The force center elimination ion of M/Z 107 is one of the most common fragments in nitazene spectra and is diagnostic of alkoxy substituents The benzylic cleavage of metanitazene gives that benzylic ion of 121, adenitazene gives 135, and proto and isodonitazene give 149. The four-center elimination of alkoxy groups results in that cation of 107, but only if the chain is longer than a methyl chain. If we look at the ethoxy substituent on adenitazene, we can see that there's 1, 2, 3, 4 centers that can participate in electron shuffling, where this bond breaks, this bond forms to create your M over Z107 fragment and ethylene. Whereas with the methoxy substituent on metanitazene, we only have 1, 2, 3 centers, and therefore no four-center elimination can occur. And that is why when you look at the benzylic cleavage of metanitazene, you only see a fragment of 121 and not a fragment of 107. Hardwick and Davidson put together this decision tree on benzylic cleavage. The first step is to identify if there is a peak at 107. If there is no peak at 107, but there is a peak at 121, there is likely a methoxy substitution. Now, the most common benzylic cleavage ions are 135, 149, and 163. Now, you'll notice that there are regioisomers for peak 163 and 149. As the chain length increases, so can the complexity of that chain, containing the same molecular formula but different branches at different points. And if you have a peak at 107 and you also see a peak at 163, this likely contains a butyl isomer. If there's a peak at 149, and this is likely a propyl isomer, and if it's a peak at 135, it's likely an ethoxy substituent, and so on. Now, I will note that 135 could also be the loss of a CH3 or a CH2 from propyl and butyl. So it's important to dig along the baseline downfield if the unknown doesn't co-elute with adenitazene. Now back to our unknown spectra. If we look here, we see that we have a peak at 107. So it contains an alkoxy group that can undergo four-center elimination, which rules out a methoxy substitution. We don't see any of these, but we do see that other peak at 153. Whatever the substitution is with a peak at 153, it has to be between a butyl group of 163 and a propyl group of 149. Now, I put together a series of possible alkoxy substituent fragments, and looking between those butyl and propyl groups, we have this fluorinated ethoxy chain that gives us an M over Z of 153. So far, we can be pretty confident that we have a diethyl substituted nitazene analog because of that peak of 86 and 58, with an alkoxy substituent based on the peaks at 107 and 153, because that can undergo four-center elimination to form that peak at 107. We have the fluorine on this terminal end of the ethoxy chain, but the fluorine could also be at the position adjacent to the oxygen as well. And this is where an understanding of chemical synthesis is very helpful. It would be quite difficult to install a fluorine here at this position, so the isomer is likely this configuration with the fluorine at the terminus of the ethoxy group. So now our next step is to comb the baseline for more important information about the substitution on that benzimidazole. And this is where pumping up the volume can help verify the substitution on the benzimidazole core. If we have an alkoxy substituted nitazene, we can figure out the substitution on the benzimidazole by combing the baseline for benzimidazole fragments from the alpha cleavage. Remember that alpha cleavage occurs here between the amine group and the benzimidazole core. The alpha cleavage leaves this low abundance benzimidazole ion and then can further fragment through four-center elimination to this phenoxonium ion. Again, methoxy groups cannot undergo four-center elimination, so 282 will not be present in the spectrum of a methoxy substitution. In our adenitazene example, the phenoxonium would show up at 282 with a nitro substituent at that 5 position. In the case of etodeznitazene with a hydrogen at that 5 position, the peak would be 237. And in 5-methyl-etodeznitazene with a methyl group at the 5 position, that peak would be 251. So far, these are the only benzimidazole substitutions we have seen so far. If we see a fragment at 282, we can then add the mass of our suspected alkoxy chain to find the alpha cleavage intermediate, in this case adenitazene, a peak at 310. Now, the reason these peaks are so low in abundance is the loss of the nitro group in favor of the stable nitro radical, and for this reason, nitro molecular ions and intermediates may not always show up. The loss of the nitro radical is the reason the molecular ion of most nitazenes are almost non-existent, while desnitazene analogs, such as the 5-methyl and the hydrogen substituted analogs, tend to have observable molecular ions. And while the nitro and methyl groups are most likely at the 5 position due to the structure-activity relationships of this compound class, it's also possible that the substitution could be at another position on the benzimidazole ring. Loss of hydrogen from these fragments is also a possibility, leading to an M over Z minus 2, so let's go back to our unknown. We have a suspected fluorinated ethoxy group, so let's comb the baseline for our benzimidazole fragments. Now at the bottom, we can see that there's the tiniest fragment at 282 and a loss of hydrogen fragment at 280. And this is a strong indicator that we have a nitro group on the benzimidazole, most likely again at the 5 position. If we look really hard, we can corroborate that fluorinated ethoxy chain because there is a peak at 328, albeit very small, coinciding with a benzimidazole ion from the alpha cleavage. There is also a teeny tiny peak at 414 here, and that could be the molecular ion. So our spectra is fluadenitazene, which is one of the latest nitazenes being marketed on direct user sites as of 2024. The structure was confirmed in May of this year by the Forensic Toxicology Department at the Institute of Forensic Medicine at the University of Medical Center Freiburg, Germany. And as we discussed earlier, that the N-desethyl metabolites are also being marketed, and their interpretation is slightly different. The N-desethyl analogs fragment in much the same way, but with an additional caveat. Now, the biggest difference in this fragmentation pathway is the base peak. We would expect to see a base peak of 58 for the alpha cleavage, but that's not the base peak in these samples. Typically, the base peak is the benzylic cleavage intermediate, and that's the most abundant fragment. The reason for this is because a competing force-center elimination pathway also occurs where the ethylamine eliminates, resulting in a loss of M57. If you add 57 to this peak, then you get the molecular ion. And while the benzimidazole alpha cleavage is low abundance, the force-center elimination fragment of the ethylamine is observed in higher abundance. In our spectra of N-desethyl adenitazene, we can see that we have our benzylic cleavage fragment at 135, and that is our base peak. We also see the benzimidazole alpha cleavage force-center elimination product, that phenoxonium ion at 282. It's much higher abundance, more prevalent than in the desethyl parents. The ethyliminium ion from alpha cleavage is the second most prevalent peak at 58. We see our force-center elimination, alkoxy force-center elimination ion at 107, and the ethylamino force-center elimination ion at 311. Now, if we add 57 to 311, we get 368, which is our molecular ion. And you can see there's a little peak right there for it as well. In contrast, an N-dimethyl adenitazene has the same molecular mass as N-desethyl adenitazene and an alpha cleavage of 58. However, the alpha cleavage forms the base peak of the NN dimethyl adenitazene, because this amine is not undergoing a secondary competing force center elimination pathway. N,N-dimethylaminoadenitazene was detected in seized samples by Latvian police in November of 2023. Hardwick and Davidson put together another decision tree based on the alpha cleavage fragmentation pathway. First, we have to ask, is there a base peak of 86? If yes, then we look for a secondary peak of 58, and if that is present, we expect to see a diethyl substitution on the ethyl amino portion of the nitazene. If there's a base peak of 86 and a peak of 58 is not present, then a different substitution pattern such as N-methyl and propyl could also be a possibility. If there is no peak at 86, but you see a large base peak at 58, then you likely have an NN-dimethyl substitution. If you have a peak at 58, but it's not the base peak, it is likely to be a desethyl substituted analog. If you see neither 86 nor 58, but you see a peak at 84 and a secondary peak at 55, you likely have a pyrrolidino substitution. If you see a peak at 98 and a secondary peak at 55, you likely have a piperidinylbenzimidazolones substitution. If you see a peak at 55, if you don't see a peak at 55 or any of these peaks, this could be a completely different substitution altogether. Here's an unknown spectra that we received from Canada Border Services in February of 2023. Using our decision tree, we see that we have a base peak of 86 and a secondary peak at 58, giving us a diethyl substituted analog. Next, we look for 107. But we don't see a peak at 107. We also don't see a peak for a phenoxonium ion, so whatever substitution we have on the benzyl portion cannot undergo force center elimination. However, we do see a peak at 133. We initially thought that this could be an isomer of propylnitazene, but the oxygen at that para position is quite important for potency of these compounds. At the time that we received the sample, we were also collaborating with Ghent University on a second round of testing, looking at the pharmacology of prophetic nitazenes. These are structures that we anticipated could be coming down the pipeline based on literature precedent. One of those nitazenes was ethylene oxynitazene. And with the permission of our collaborators, we sent over a standard to CBS, and they were able to form a match. We can see a peak at 306 and a possible loss of hydrogen from our alpha cleavage, as well as the molecular ion at 394. And here I'll walk you through a recent unknown that was sent to my colleague Nathan Lale in January of 2024. Tom Black from Ohio BCI had a seized sample that didn't colute with adenitazene, protonitazene, or isodonitazene. He sent over the spectra to Nate with a suggestion that it might be 6-methyladenitazene. The mass had an additional methyl group. We looked at the spectra and we were kind of stumped at first. It had all the hallmarks of adenitazene. And based on the retention time of the unknown, we thought that it could possibly be an uncyclized intermediate of either adenitazene or isodonitazene. So we sent over the standard, and when it was tested against the unknown, the GC mass spec looked similar, but unfortunately it wasn't a match, and it was quite far off. So we were back to square one. So let's go through and analyze this compound again with our decision tree. Now looking at the spectrum, we have a base peak of 86, and then we have a secondary peak at 58, which indicates that we have that diethyl substitution on the ethyl amino portion of the nitazene. If we look, we see we have a peak at 107. We go down the line, we see we have a peak at 135. We don't see a peak at 163 or 149. And this suggests the ethoxy substitution on that benzyl portion of the compound. Working with BCI's suggestion that there was an additional methyl group, we would expect the following ions to show up. When we pump up the volume, we can see a very small peak at 294, which could be the phenoxonium ion of 296 minus hydrogen. and a peak at 324, which could be the benzimidazole alpha cleavage ion. And then there's also a decent sized peak at 250, which could be the loss of the nitro group. One thing to note that there is often a fragment of 207 in the nitazenes. It's a common fragment, but we're not quite sure what it is. And then if we look downfield, there is another possible ion that could be the molecular ion at 410. So based on what we have here, it seems plausible that there could be an additional CH3 or CH2 group somewhere on the nitazene. Based on the spectra we received, we have a diethyl substituted amine, an ethoxy substituted benzyl substituent, and a possible addition of a methyl or a methylene group somewhere on the molecule. And while the 6-methyl adenitazene makes sense, it's not the only possible regioisomer. There are at least 6 other reasonable structures with the same molecular formula. Protonitazene and isodonitazene were eliminated at the get-go with standards. We also have a methyl that can be located in the 6, 4, and 7 position on the benzimidazole, and also 2 other options where the methyl can be added to the benzyl substitution as well. And when we receive an unknown, here are some of the things that we consider when we propose a structure. Let's go back to our synthetic route. The first thing we do is look to see if there are any starting materials for the final compound that are widely available and cheap in bulk. We can pretty much eliminate the starting materials that cost over $200 a gram. Clandestine chemists are making these on a kilogram scale, and this would be very cost prohibitive. And that eliminates the 4-methyl, 7-methyl, and methylbenzyl adenitazene, narrowing it down from 5 to 2 options. The most likely structures are the 6-methyl adenitazene that was proposed by BCI and ethylene adenitazene. Ethylene adenitazene was another prophetic nitazene our collaborators at Ghent University had considered. Our in-house GC mass spec resembled the unknown, and the structure had also been published with 50 times the potency of morphine in a medicinal chemistry book in the late 1960s. And from a synthetic standpoint, it's also cheaper to use a large bulk intermediate and swap out the benzyl substituent in the last step versus going back 2 steps and creating a new benzimidazole core, especially if there's no literature precedent for its potency. So this made the ethylene adenitazene the most likely structure for the unknown, and with the permission of our collaborators, we provided the standard. And when they tested the sample alongside the ethylene adenitazene standard, the retention times matched. The length of the chain between the benzimidazole likely fragments to form the same major peaks as adenitazene. If it cleaves here, then we also see our peak at 107 and 135. In summary, here are the major takeaways of interpreting nitazene spectra. Spectra with a large base peak ion of 58, 84, 86, or 98 are likely the alpha cleavage of a disubstituted amino analog. A large base peak of 58 indicates a dimethyl substitution on the amino portion of the nitazene, while a base peak of 86 in the presence of a secondary peak of 58 indicates diethyl substitution on the amino group. A base peak of 84 in the presence of a peak at 55 indicate a piperidinylbenzimidazole analog, while a base peak of 98 in the presence of a secondary peak at 55 or 70 indicate a piperidinylbenzimidazole analog. N-acetyl analogs are the exception to that base peak rule. With a lower abundance alpha cleavage peak of 58, it is not the base peak because of a competing pathway where the N-ethyl substituent undergoes force-center elimination to form that peak of M-57. The base peak of N-acetyl analogs is from that benzylic cleavage. A loss of hydrogen is possible for most, if not all, these fragments, resulting in an M over Z minus 2. Higher fragments in nitro-substituted analogs may not be present because of the loss of the stable nitro radical, which is why the molecular ion may or may not be apparent in nitro-substituted analogs. Desnitazene analogs exhibit a molecular ion higher than 1% abundance, because of this. They don't have to worry about that loss of the nitro radical. There is also a possibility of multiple isomers, and when there are additional substituents on the benzimidazole and longer chain substituents are present on either or both the benzylic and amino portions. So other methods are required to differentiate these isomers, such as retention time. With the exception of the N-diethyl analogs, the benzylic cleavage is usually the second most common fragment. If a peak is observed at 107, it is likely from an alkoxy substituent at the para position of the benzylic portion of the molecule. Look for another ion downfield and subtract 107 to find out the formula of the substituent on the oxygen. If a peak is observed at 121 and there's no peak at 107, then you likely have a methoxy substituent on the benzyl portion of the molecule. The most likely position is the para position due to the pharmacology of the compound. If the phenoxonium ion is present, it can give indication of the substituent on the benzimidazole group. So far, nitro, methyl, and hydrogen substituents are the only ones observed on direct-to-user sites. At this time, I'd like to provide a snapshot of the next scaffold that is currently emerging in opioid samples. We call them the orphines. The orphines were originally developed in the 1960s by the research lab of Dr. C. Jensen for their anesthetic and antitussive properties. Bezitramide is a potent opioid that was marketed in Western Europe under the name Bergoden for severe chronic pain. In 2004, it was removed from circulation in the Netherlands due to multiple overdoses and was never marketed in the United States. In an effort to identify safer analgesics, the mu-opioid receptor activity of the orphine scaffold was reinvestigated in 2018, and 2 years later, brorphine emerged on direct-to-user sites. It was also found in seized case samples and was marketed as purple heroin and cut into fake oxycodone tablets. In the medicinal chemistry paper here, you'll also notice that in addition to the brorphine analog, there's also the chloro and fluoro analogs as well. Those analogs began to emerge on direct-to-user sites in 2022. Their naming appears to be based on brorphine, where they swap out the bromine for an iodine to create iodorphine, a chlorine to create chlorphine, a fluorine to create fluorphine, and omitting the bromine altogether to create the scaffold name orphine. Now, another compound that was in the 2018 medicinal chemistry paper, SR17018, was also found for sale on direct-to-user sites and was first identified in a sample by the CFSRE in May of 2024. Cychlorophene, another analog, was found for sale on direct-to-user sites in January of 2024, with the CFSRE reporting one case in Q3 of that year. Now, our naming collaboration has attempted to work with the orphine naming system to rename SR17018. And if we look at the scaffold, we have chlorphine, but it's missing the methyl group here. So it makes it a des-methylchlorphine. And if we start the numbering position here at N1 with the nitrogen that can be substituted and walking counterclockwise, we have positions 1, 2, and 3, 4, 5, and 6, and then 7, making this 5,6 dichloro-desmethylchlorphine. Same thing with the cychlorophene. We have the chlorphine scaffold, and N1 is substituted with this propionitrile group, making it N-propionitrile chlorphine. Spirochlorophene has recently emerged on direct-to-user sites at the end of 2024. It was originally published as R6890 in pharmacology papers in the 1960s. It was brought up on discussion boards in 2020 and in 2023. It began showing up on trip reports in 2024. And then as early as Q1 of 2025, 5,6-dichlorobrorphine began popping up on direct-to-user sites, and that standard is about to be released. We just recently released bizitramide and its active metabolite, despropionyl as well. So these are some of the latest opioid scaffolds and standards to be on the lookout for in your forensic case samples. We have a number of resources available on our website to assist with the identification of unknown spectra. If you follow this QR code, this will take you to our GC mass spec identification tool, where you can filter your data by formula weight, base peak ion, and secondary base peak. That will bring up the compounds in our catalog that match those queries, and then you can view our GC mass spec data PDFs by clicking that little blue button. We also offer our GC mass spec library completely free of charge. So that is available for download as well. Here I have our NPS snapshot of the nitazenes. This will give a quick view of all of the nitazenes that are available on our website, as well as their CRMs and regulatory status. But of course, there's always new standards coming up all the time, so do be sure to check the website. You can find the latest nitazene analogs in our catalog by following this QR code, as well as the latest orphines by following this QR code. We also keep an up-to-date living document on the quarterly scope recommendations of the CFSRE and Soft NPS Committee. We highlight those items that have changed tiers, as well as provide links to the parent standards, their CRMs, and metabolites as they come out for a one-stop shop experience. And if you follow this QR code, that will take you to that article. At this time, I'd like to acknowledge the hard work of our collaborators at Kent University. We have Dr. Marta van de Put, Dr. Kathleen van Outfunge, and Dr. Christoph Stove. It's amazing work that they contribute to this field, and it's crucial, and it's been an honor to work with them on these projects. I'd also like to thank my colleagues at Cayman Chemical. I work with a fantastic group of scientists. This is Dr. Donna Ayula, the VP of Forensic Chemistry, Nathan Lale, who I work with closely on the nitazene product line, Dr. Camille Watson-Gooden, and Holly Pierzynski, who are our GC mass spec experts. Holly oversees the GC mass spec unknown program. I'd also like to acknowledge and send a special thank you to Emma Hardwick and Tyler Davidson for their amazing work on nitazene fragmentation patterns that I presented today, as well as Alex Kratalski from the CFSRE for his contributions to the nitazene nomenclature, and of course to those who are willing to share their unknown data with us. Thank you to Tom Black from Ohio, BCI, and Canada Border Services. And thank you for attending this webinar. If you have an unknown in your casework, please don't hesitate to reach out. You can email our tech support team at techserve@caymanchem.com. If you have any questions related to the webinar or an unknown, you can also reach out to me directly at dstgermain@caymanchem.com. Thank you again, and have a lovely day. We are an analytical reference standard provider and offer a wide variety of novel psychoactive substances, phytocannabinoid, and mushroom components for cannabis and forensic analytical testing. We are also accredited under ISO 17034 and ISO 17025. We are an industry leader in lipid biochemistry, endocannabinoid chemistry, and novel psychoactive substances.